We want to change problem number 8.
Problem number 8.
Okay. Okay, so we want to change problem number 14, ruler trick.
Present the challenge.
So we will accept the problem is number 14, and so all the team please send your team members to write on the memo. check off your mark the later.
Place a ruler on the edge of the table and throw a ball at its free end. The ruler will fall. However, if you cover part of the ruler with a piece of paper and repeat the throw, then the ruler will remain on the table while the ball bounces. Explain this phenomenon and investigate the relevant parameters. So due to the problem statement, we will mainly focus on why will the ruler remain still on the table and the critical conditions of this phenomenon. And it is my outline. I will first talk about the preliminary experiment, and then it's my theory, including Bernoulli's principle. Then in my experiment, I will talk about my setup parameters. And next is a discussion, and finally is a conclusion. At first, I want to show my observation videos. As you can see, the two videos are all both covered by the A4 paper. But at the left-hand side, when we throw a ball very low, the ruler remains on the table. While we throw it from a higher position, it will remain on the table. So we think that it must be some air flowing from the paper. So we spread some styrofoam crumbs around the paper. And the air will be sucked under the paper. As you can see, the styrofoam crumbs will be sucked under the paper. So we can make sure that it is ready for Bernoulli's principle. So to explain this phenomenon, this is the simple model of my experiment. But the ruler didn't receive any force, it remains still on the table, just like this. When the ball falls on it, it tries to lift up against the paper and causing the volume underneath to increase. Due to Bernoulli's principle, the air will flow into space under the paper, so that the air pressure on the paper will decrease and leading to a pressure gradient. It will lead to an atmospheric pressure to press the ruler and balance the torque on the ruler. You see from a cross section, while the paper is lifted by the ruler, the air will flow under the paper, so it will generate a lower pressure gradient. So we combine the Bernoulli's principle and the adiabatic process and leading to a formula of the pressure difference and the airflow velocity. To make sure it is ready Bernoulli's principle, we design two packing plates placed by straws. One is ratio one and one is close arrangement one. While the ratio arrangement one allows air to flow in faster, so it will lead to a higher critical height. When the airflow and the volume under the paper increase and lead to air pressure to decrease, so it turns out that the ratio arrangement's critical height is really higher than the closed arrangement one. So we can make sure it is ready Bernoulli's principle. And for a basic assumption, we use the Bernoulli's principle, and we assume that this process is under adiabatic process since the time for the air to flow in is too short. So the heat exchange in that time can be negligible. And meanwhile, the gas expanded under the paper can be less. There's no heat exchange. And for the ruler spinning part, we use classical wind theory. And for the V1 is the velocity of the ball, and V2 is the ruler velocity, which is covered by the paper. So when we calculate the two positions of two sides of a ruler, we can get a ratio of V1 and V2 as 5. And the actual experiment data is 4.71, so it's actually quite matched the theory. And we can simplify the formula of the pressure change and the airflow velocity. And we assume that the velocity of air is beta times V2. So that after we calculate the pressure change, we can lead to beta, so that we can calculate the effective velocity of the airflow. And for experiments, firstly, I'm going to talk about my setups. We use electromagnet to assay our releasing device so that we can release the ball without contact and reduce the deviations. And we also use adjustable discs that we can control the releasing height. So all we need to do is turn on and off the electromagnet and until the ball fall on what we want. And our first parameter is the length of the paper. We define the length of the paper five sizes from 25 to 29 centimeters. And we measure the critical height under these circumstances. And we control the outer length of a ruler and the width of steel balls and paper. And this is a chart to show if the ball mass and the paper length change when the ruler still remain on the table or not. And when the ball mass will increase, it means that the force it provides to the ruler increase. So it will be easier to smash down. But when the paper length increase, it means that the torque provided to the ruler increase, so it will be harder to smash. And this is a critical height under our parameters. And when there is a heavier ball, it means that the torque provided to the ruler is higher, so it will lead to a lower critical height. And when there is longer paper length, the force arm is higher, so it will lead to higher critical height. And similarly, we change the width of the paper to four sizes from 5 to 20, and also measure critical height. And this is also the chart to show whether it will fall or not. And the result is similar to the last one. When the ball mass increase or the paper width decrease, it will be easier to smash. And this is also the chart to show the critical height under different paper widths. With a heavier ball, it will have lower critical height, and lower paper width will lead to higher critical height. And our next parameters is that we change the weight of the balls to five sizes from 32 to 110 grams. And we also measure critical height, but we use A4 paper now. And as you can see, the trend is cooling down, and because when the ball mass increase, it will provide more force to the ruler so that the critical height will be lower. And for our ruler protrusion, we change it to four sizes from 14 to 20. And we also measure critical height and use the ball that weighs 88 grams. The critical height under different ruler protrusion is just like this. It's similar to the last one, the width of the ball, because the force arm is lower, so the critical height will be lower. And despite those parameters, there's also something that we can discuss about. One is falling point. We define our falling point as the end of the ruler to the point we fall on, to five sizes from 2 to 14. And we also measure critical height. Not as we usually think, the critical height can't increase, but first rise and down. It's because when we fall on a point that is closer to a table, the force arm will decrease. It means that the torque provided to the ruler will decrease, so the critical height will be higher. But when we fall on a point that is really close to the table, it means that we can treat the ruler as a hook. It means that we just lead the paper directly, so it will lead to a lower critical height. When we combine these two factors, it will first rise and down, just like this. And for the bounce height, we compare the bounce height and the releasing height to conclude the ratio of the velocity and the ball velocity and the ball's bounding velocity. And so that we can measure the velocity change of a ball and calculate the airflow velocity. For the conclusion, the first point is why doesn't the ruler fall off? It's because when the ball fall on the ruler, it tries to bounce against the paper, so the airflow will flow in. So due to the Bernoulli's principle, the air pressure will decrease and provide the torque for the ruler to balance the ball's force. And the second point is the critical conditions. As you can see, the paper size can really affect the phenomenon. And also the ball mass and the ruler protrusion. If the ball mass is heavier or the ruler protrusion is smaller, then the critical height will be lower. And for the next one is the critical height when the ball hits on different point on the ruler. And the point hit on the ruler is closer to a table, then it will first rise and down. It's because the ruler's
paper in your theory? Yes?
No.
No. Okay. Then you consider the deformation of your ruler
Yes.
in your theory?
Yes.
Yes. Okay. So do you change the elastic coefficient or you just use the same?
We use same ruler.
You use the same ruler. Okay. Then do you consider the contact time of the ball?
Yes.
Yes. Okay. Then do you consider the deformation of the ball since it just bounced on the
Oh,
ruler?
we use steel ball, so it's rigid.
Okay. Then how do you define the height?
The height
From the max point of the ball or from the
from
downside
the
of the
bottom of the ball.
from the bottom of the ball? Okay. Then what's your method you place the paper? You just set the mass center or you set the edge from the you set the distance from the edge to the ruler, the sound point of your ruler.
Can you explain?
So you you set the end of the ruler on the the mass point, or you just set the edge and the end of the ruler just in certain distance.
Like the outer length of a ruler is 20 centimeter, and the inner length is also 20.
Okay, time's up.
他头已经关起来，你开一下。
它是自动。干什么掉？You want to start now?
No, wait.
started studying stage?
I'm the opponent of TYPT. My name is Chen Sun. Today I'm going to talk about problem number 14 relaxation. So here's the summary of the report. First, in their report, they use Bernoulli's principle and adiabatic process and a classical beam exchange. And in conclusion, they explain why the ruler did fall when it is placed with the paper and the physical conditions like the height or the mass. And here's some strengths and results of improvement of reporter. So first, they highlighted the main point in the problem statement, which is very clear for us to know about what the problem wants us to know. And it has clear diagrams with clear explanation and clear theory. And it explains the experiment very clearly, so we know how they do the experiment and have created diagrams. But the area of improvement, lack of explanation in formula, lack of measurement including air pressure, since they said they didn't measure. And there are some experimental details missing in the presentation. And they measure the height of the ball using the bottom, but according to their relation, they define the height of the ball as they define the point of the height of the ball is the mass center. So I think it's not very adequate. And the flaws in the experiment. So here's some point of discussion that we will discuss later. So first, the problem statement is which parameters that affects its ball or not. And in a theory, it's about like pressure as a function of paper and ruler, and an elastic coefficient. And how does it list those parameters affect the experiment? And in the experiment part, we want to discuss about the time, like force action on the ruler, which the reporter said they considered, but they didn't talk much about in their report. And they discussed the bending on the ruler, which opponent and which reporter said they considered the bending of the ruler, but it didn't really tell us how does it affect. And the energy loss increased the critical release height, which is I was very curious about. And the elastic collisions, the formation of the ball, and the vacuum chamber. Okay, so I think we can go through the discussion. Okay, so first, reporter, you said you consider the contact time, right? So in the same mass or same force, when the contact time is longer, how will the ruler be easier or harder to fall?
When the contact time is longer, it means that it has more time for airflow to flow in. So the velocity of airflow will be slower, so that the critical height will be lower.
Okay. Then you just mentioned that you consider the bending of the ruler.
Yes.
Right? So how will it affect your result?
If your ruler is more elastic, it means that it will lead to a lower critical height.
Lower why?
Because if the ruler needs to bounce off the ball, it will provide energy to the ball. No, the ball will provide less energy to the ruler, so I meant my answer, the critical height will be higher.
Sorry again. So in what condition the critical height will be higher? So more or less elastic condition?
If your ruler is more elastic, then the critical height will be higher.
Okay. Then so continue to the benefits of the ruler. So in my opinion, I think when can you time is the blackboard? So here's my ruler test, and I put my ruler here. Okay. So And so when it's more elastic, so is it longer or shorter time for the energy to go from here?
If your ruler is more elastic, then that is more time, because if your ruler will bend like this, and it needs time to transfer the energy to the end of the opposite side of the ruler.
Yes. So since you just said, so when it's more elastic, the boundary height will be higher, right?
Yes.
Yes. But you said the time will be longer. So the longer time that the force just act on the paper, the lower critical height. But so it's just like it's just like
But when your ruler is bent like this,
yes.
it needs time to transfer the energy to the opposite side. So the paper has more time to press the ruler down. So the critical height will actually be lower.
So higher or lower? What?
If your elastic ruler, if your ruler have more elasticity, then the critical height will be lower.
Okay. But okay. So you said that the air pressure and made it hard to live off.
Yes.
Right. So when you just mentioned that when we bend the ruler, then the paper will just like deform to like this.
Yes.
This shape. Yes. So the area will change, right?
What area?
So since the paper is flat
Yeah.
and this part is go up, so the total area will decrease, right?
What area?
Okay, so the force that air just acts on the paper, you can T times A,
Yes.
the area of the paper. But when my paper just like shape like this, so this part will just go in a little bit, right?
Yes.
Go in a little. So the total area that I just see, so if I observe here, my area will go like this. Do you agree?
Yes.
Yes. So since the area will go, the area will decrease. So does it affect much, or do you think it didn't affect?
I think it didn't affect much because we use Bernoulli's principle. And the emphasized part is the part which is under the paper, because the volume under the paper increased, so that due to the Bernoulli's principle, the air will flow into the volume under the space under the paper, so the pressure will decrease and lead to a pressure gradient, so that the atmospheric pressure will pass the paper.
Okay, so you just mentioned the pressure gradient, right?
Yeah.
So like okay, so I observe from here, so can you show how pressure from high to low inside the paper? And you said like it will suck the air into the chamber.
Yes.
So there might be the it might be the distribution of the air pressure.
Yes.
Can you describe it?
This is your paper and this is our ruler. If your ruler is your ruler length is close
but so it means if the edge of the ruler just goes off the half side, the paper will just bend like this. Right, since you said the air is going from here to here.
No,
Right.
the paper will be like this. This is the ruler, and it will lift up the side of the paper.
Yes, but you said here the air is coming from. Right. So okay, so how about change some? Okay, so I want to ask about how you put your paper. Since you said in your ruler and here's your ruler and here's your paper. You said here is 20 centimeters
Yes.
and 20 centimeters, right? So when you change the area of the paper, you just said in your report. So is it still 20 and 20?
Yes.
Yes. So you said the force effect on the ruler. How does it affect? So since the force will put on the ruler like the smaller paper image like on the center on the edge of the ruler. But when my paper goes bigger, the force center may be off of my ruler. Yeah. Right. So how does it affect?
I think that the air pressure are equally. So
Equal.
every part has atmospheric pressure to pass the ruler.
But so you said equally in so the force that the ruler will receive just the area here. But since you said the air pressure is equal, so it means that the force that I add on the ruler only this area.
If you mean just act on the ruler, yes.
So but when you change the area of the paper, right, then the boundary height changes. So how to tell it? Since you said it's equal.
Because if the paper is much bigger, then the angle is will be lifted up as smaller, so the space for the air to flow in is
So sorry. So you said you have the same distance,
yes.
but the bigger paper and the force I just act on this point when my ruler flip up. So the angle may be the same.
Now, if your paper is bigger, then it is harder to lift up.
Since there's this, so at the very beginning of the motion, they didn't have the variation of pressure, right? So at the very beginning, it didn't relative. So if it is hard or easy to lift up, it didn't relatively relate with the area of the pressure. The area of
Okay, time's up.
You have 1 minute to summarize.
Okay, so in our discussion, we discussed about the contact time. With the time, just longer the airflow to get in, the critical height will be lower. And after we discussed about the bend of the ruler. So if the ruler elastic go up, the critical height is go up. And next we discussed about the differential of the paper. So according to reporters theory, they use Bernoulli's law, so you don't need to measure the area, but the reporter just mentioned the variation of area in their experiment. And next is the change of the papers. So since the ruler is 20 inside and 20 outside.
Hi, I'm a reviewer for Team Relativity, and I want to ask the reporter, you use Bernoulli principle in your theory, but Bernoulli principle could only be used in steady flow, but in your model it's not. So what do you think about, what do you think physically this principle is right?
Yes, but because the airflow is static.
It's flowing from every side, it's not like a tube, not steady.
But it only can make sense when we want to let airflow in and the pressure decrease, we can only use the wall principle.
What does the point think?
I didn't agree with Porter since like the river just mentioned the flow isn't a static flow, and in a way the airflow isn't the same.
Okay, and I want to ask the reporter and the opponent, in what condition will the air pressure increase and decrease? What parameters? What parameters increases the air pressure or decreases?
What part of the air pressure?
For the entire model.
If you have higher temperature or like you change the humidity, it's of course that the air pressure will be higher or lower.
What does the opponent think?
I agree with the reporter, but I think reporter have to fix their experiment till they fix their air pressure in their experiment.
Yes. Can you calculate the critical value and compare with the theory and experiment?
Yes, we have calculated, but we didn't show it in our report.
And can you describe it a little bit?
It is quite, our experiment is quite matched to the theory.
So you use Bernoulli to calculate the theory.
Yes.
Okay. Do you think, I asked the reporter, do you think if the ruler is when it gets a bigger hit with the ball, it will cause a bigger air pressure difference because the air pockets form faster?
You mean when the ball is heavier,
Yes.
then the contact time will be shorter, so the airflow velocity under the paper will be faster, so it will lead to a higher critical height.
What does the opponent think?
I agree with you.
Okay. So do you think the entire paper will get from the air pressure, like the entire paper in the experiment, will get all air pressure on it?
Yeah.
What does the opponent think?
Yes.
Okay, thank you. That's my question.
So you have 2 minutes to prepare.
Hi, I'm the reviewer from Team Activity. And here's the problem statement. So you place a ruler on the edge of the table, throw a ball at the end, throw a ball. What However, if you cover it with a piece of paper and repeat the ball will bounce off. And you need to explain this phenomenon and investigate relevant parameters. So here's a summary of the report. So the reporter talked about using air pressure and with Bernoulli's equation to know the air pressure, and then use pressure gradient to let us know, and beam exchange to talk about the ruler's deformation. And in her experiment, she uses different parameters such as the weight of the ball, the bounce, release, and bounce height, and the length and width of the paper, the ruler protrusion, and the falling point. And in her setup, she uses a magnet to control the same dropping spot. And the reporter, I think he has a complete quantitative phenomenon explanation, and she also has a lot of experiments to prove. And I think she has a great assumption and amazing modeling on ball drop. And then she has a simple physics explanation, but I think she has a lack of quantitative comparison between theory and experiment. And she said she had done it, but haven't put it in the report. And then she didn't explain the importance of air pressure and how it's calculated. And I think it's model and theory doesn't match really well. And for opponent, I think he has a good understanding on the problem, and then he has a good remark and tells all about what's happening, and he has his own opinion, and he has a good understanding on the questions. And here's my point. So maybe she could use maybe like Navier-Stokes equation to do some simulation. So from a simulation that's done, the air pressure could be calculated, and she could actually calculate a different amount of different air pressure on each spot by using software such as Flow3D. And I think these are missed points in the discussion. So I think she maybe could use some actual torque calculations by using the ruler's weight, the ball's weight, the paper's weight to calculate the actual value, and then the air pressure actually changes in different parameters, and I think she should do more explaining on that, and mostly important, the calculations of the air pressure. So here's a discussion. So the opponent said, did you measure the air pressure? And the reporter said no, but it's possible to find comparing the torque and the actual results. And then the next question is about, well, what happens when the contact time is longer? And of course that it will be easier to fall due to the air pressure, but even though that's true, but it's not the full thing on it. I think if you contact longer, the force will be separated and it might not fall off instantly. And then here's the next question is there's more elasticity with far higher, and the reporter has two answers, but so I don't understand. I think you should tell us completely. And the next question is about the air pocket, which affect very much on the experiment. And then the reporter says it will change because of Bernoulli's principle. And then I think Bernoulli's principle wouldn't be very good fit in this phenomenon because it's not a steady flow and it's not possible calculating only by Bernoulli's principle. And then one has the paper error relation with air pocket, and I think the air pressure due to the air pressure is equal, and I think it's not because some places will have higher pressure and some places will have lower pressure. And then I asked, is it good to use Bernoulli's principle? And the opponent said agree to the reporter, but I think it's not a complete explanation on this entire phenomenon. And then I asked what the temperature. I asked if the reporter said when it's hotter, the air pressure will be higher, but I think the temperature is not the most important part here. And then I asked the critical value, and the reporter said use Bernoulli's principle. I think it's very hard to calculate. And here's my presentation. Thank you.
So we probably have 2 minutes to
So I'm going to talk about my concluding remark. And we think that for elastic ruler will lead to a higher critical height due to the energy exchange. And we calculate our elasticity of the ruler by the bouncing height. And it depends on which one side of the paper is closer to a ruler that affects more in this phenomenon. And the force acting on a different part of the ruler is related to a torque, because the force on our train. And the length of the paper will affect the torque. So the result is different to the ruler protrusion. And a deformation causing change of air pressure doesn't affect much in this theory. And if the airflow velocity on the paper is higher, it will be harder to smash down into our theory. And we think that the Bernoulli's principle can be a correct assumption is because that we designed two pending plates. One ratio one can allow the air to flow it's really Bernoulli's principle, then the ratio arrangement one should have a higher critical height because the volume on the paper increase when the airflow in very fast, the air pressure will decrease. So it will lead to a higher critical height, and the result is really just like this. Thank you.
So we have 5 minutes for the jury's last question. Okay, continue.
I have a question for 3 groups. So if we change the paper to like cardboard paper, like what's over there, we will ruler 4 or for 1. So maybe start from the
Can is that your question?
So we change to very thick paper, cardboard paper.
If a paper is thicker, then it is, and then it will be harder, and the mass will also be larger, so it will lead to a higher critical height.
So I think when we change to like this kind of paper, it's been like harder to deform. So the variation of air pressure won't be very like it won't be very big. So I think it's easier for the ruler to label.
If the mass is the same between the two materials paper, I think the harder paper will have it will be easier to flip because the harder paper will be harder to form an air pocket, and these kind of paper will form an air pocket very easily, and it will be a very bigger air pressure on this.
Okay. Any other? Okay, Professor, please.
Okay, you will talk about several factors affecting the holding ability. You talk about the height, the weight, and also the elasticity of the ruler. But these are not the real factor. What is the exact physical parameter affecting the holding ability?
It's because the pressure gradient.
What is causing the pressure?
Because of Bernoulli's principle, when the air flow into the space under the paper, then the pressure will decrease. So there's a pressure difference under the paper and above the paper.
No, I'm asking it, what is causing the flow to be different?
Causing the airflow to be different.
Yeah, the airflow different will causing the given pressure. This is understand. But what is controlling the airflow to be different? What made the airflow to be different?
The main reason for that is because the inside of the paper, which is the air pocket, is pressure difference with the outside. So if the air pocket is flowing very fast, the air outside will want to flow in very fast. So it would depend on inside air pocket size and air pocket pressure compared to the outside.
So I think it's the time duration that forms the air pocket. So same as the reviewer.
So what is affecting the time scale to form the air pocket?
Can I answer? It's based on how fast the ruler got lifted up. So it will form either in a very slow way or a very fast chamber.
It's also related to the contact time of the ball and the reviewer. If the time is longer than the airflow, in time is longer too.
I think it also relative to how soft the paper is. So since the paper is softer, then the speed that it forms the pocket would be like it will easier for it to form the pocket, air pocket. So it's harder for it to fall.
Since all of you agree on is the time scale, but what determines the time scale? Because for example, how the time scale related to your critical height and weight and elasticity?
Excuse me?
Do you think that the factor affecting the ability to holding is the time scale? But in your experience, you talk about the critical height. weight and indexity. What's the relation between that scale?
When it reaches critical height, it means that the airflow velocity is big enough it's slow enough to count in the paper. And when the airflow velocity is slow, it means that the time is bigger.
Okay, time stop. We have a camera over there, so please show your score. So for both and be able to record your score. Let's show the score. 77677. And then the score for the opponent. 67976. And then score for the reviewer. 68877. So we have another 10 minute break.